So welcome everyone to our algorithms lecture. And today we will do a little bit of change compared to previous years because in the order of the topics we are covering. Good morning. So we'll look more into geometrical algorithms since we are going to do a midterm next week, right? Which will cover our basics or greedy algorithms or dynamic programming, again divide and conquer, of course. The other big part of other topics will be basically based on graph algorithms. So graph algorithms will be after midterm. So all the shortest path problems we will do after the midterm, right? So today we will look at some maybe we'll get more practice for the midterm. So again, the algorithms midterm will be the next Tuesday in a week, right? I know some of you might not be able to make it. I understand that, so you'll be able to make it up in the week after. And and there's some other topics which are not crucial, such as linear programming, which is an interesting topic itself, but it's not really as far as solving problems on your own. It's not really going to help you. So that's going to be left for later on in the course. So I'm rearranging the topics a little bit. So if you looked at if you're reading linear programming before, that's great, but it's not going to be covered for the midterm. It's not going to be covered. So we will look at the divide and conquer. Again, the approach of dividing, of course, our problems in smaller subsets, and how it applies to how can we use to solve geometric problems. So geometry, of course, we're all familiar with it, right? So let's see how to set up first, right? So we'll go to our course repository, right? And we'll open a code space. Hopefully, yeah, there it is. And also, of course, there's also there's notebook here, right? Topics, geometrical algorithms. Let's see here. And geometrical algorithms are here. Let's see if you need to restart the notebook. Hopefully not. All right. So it is a subfield, of course, in algorithm design. Focused on problems related to geometry, so spatial relationships, so it will necessarily involve points, lines. Again, of course, why do we need these? Of course, pretty much everywhere. Computer graphics, gaming, geographic information systems, of course, robotics, pretty much everywhere. Right. Again, the good news, of course, is for you, if you actually happen to be in a position where you need to actually implement something, of course, you would probably use a library or you would look it up, right? Here we are sort of like going through what was involved in developing these algorithms, but of course in real life you would probably use, you would read up on existing solution. That's what usually happens these days, right? But maybe we would come up with some new approaches as well. That's completely possible, right? So there's many different problems. Convex hull we'll probably look next on Thursday. On Wednesday. No, Thursday. Sorry, on Thursday. That meaning 2 days. Line intersection, closest pair of points. We'll definitely look at closest pair of points problem, which is probably one of the simpler ones. So you have some points in a plane, and you want to find out whether you see guys here. And you see, yeah, you see, yeah. So which points are the closest by Euclidean distance, right? So that's a good application of divide-conquer algorithm. There's some other ones. Again, minimum spanning tree we'll look at, of course, as part of graph algorithms. So those will be, of course, will be used later on, right? So closest pair of points problem, right? It's a classic, right? So you have a whole bunch of points, and well, which ones are the closest? So how would you solve this if you did not know anything about algorithms? I mean, you had very basic knowledge, So how would you solve this? Well, by brute force. What would be the brute force approach?
What's the format of the given points?
So xy. It's a tuple of xy. So coordinates, you have a whole bunch of points. Which ones are the closest?
I guess get the subtract From each other and check everyone.
Yeah, you have to check every point A is point B, point A is point C, and point B is point C, of course, as well, right? So, how much again? So complexity, well, it probably tells you here already. It tells you it's quadratic, right? If it's brute force, right, it's most likely quadratic, right? If you're checking everything, right? Because you have n points, right? So the point, the nth point you have to check with n minus 1 points, right? And then you keep going down, and it comes out to be, the formula comes out to be n times n minus 1 divided by 2, I believe, right? Yeah, so you have to check, right? You have, let's see, what's the formula? So you have A, B, C, D, right? So A has to be checked with, with B, C, D, right? B, C, D, right? Then you have to check B with C, D, right? And you have to check D, C with D, right? Those you have to check, right? Of course, it doesn't matter. Direction does not matter, right? So how many is there? 10, right? So it's 10, right? So 10, so 4, so let's see the formula. So it's 4 times 4 plus 1 divided by 2, right? So that is, so n times n plus 1, right? Divided by 2, right? And that's 10, right? In this case. So that is what? That is n squared plus n divided by 2, right? Yeah. So what kind of, this is complexity. What complexity? Which, this one?
N squared.
Yeah, it's n squared, because again, we care about the most one, about the most critical part here, right? These, again, even though we're dividing by 2, right? That does not affect complexity again. It's nice to be divided by 2, right? Instead of multiplying by 1,000, right? But as far as complexity analysis, it does not help us, right? So, yeah, so it is n squared. So we have a couple of approaches, and again, we'll look at divide and conquer. Turns out there is a simpler way of, well, not, I wouldn't say simpler, more efficient way. It's not as simple, unfortunately, right? And there's also approach is plain sweep, and also the Delaunay triangulation approach, right? So, well, again, how do you solve this problem? It depends how many points you have. If you have 100 points, you need to do roughly, I don't know, about 5,000 calculations, right? Not a big deal, actually. 5,000 calculations will work. So 1,000 points, roughly 500,000. Probably still with brute force, it might be simpler, right? If you actually, right, you have to do it, right? You have to solve this problem, and you don't have a ready-made approach, brute force for 1,000,000 points, 500,000 is probably like, I don't know, probably a second or so. We'll see, right? We'll try to generate some points and see. Of course, it also depends what kind of, is it the integer only coordinates, or maybe floats, maybe a really large range, right? But yeah. So of course, distances we calculate using Euclidean formula, the square root of, we know the formula, right? So we'll look at the brute force first, right? So let's do, let's do a brute force first, all right? And let me see, select kernel. Do I have kernel? I have kernel, that's great. Let's start, see if I have any, I have to start this, reload window. Let's do it. So this is outline, right? Closest pair of points using divide and conquer, but I'm going to use first mark down closest pair of points. Closest pair of points using brute force, right? That's our, right? Let's start with that. So let's first let's make a generator for our points, right? So for our n points, right? So with x and y coordinates, right? Of course, we could just make it, randomly, but let's make a function. So n points, right? Will yield, right? So yield actually, that's not a good generator. Of course, this will give you. It's a nice actually. Do you know what yield is? Actually, anyone about Python remembers what yield does? Anyone? You guys covered this in class? It basically gives you on demand. Basically, you don't get all of the points at once. You basically, it's like a range. It's kind of like your own custom range, basically. You could think of it as that way for now, right? But okay, but the problem, of course, with this approach is, of course, I'll make it a little bit bigger so you can see what's happening, right? So this is a little more, come on. Yeah, come on, plus 120. Okay, that's better, right? So, but we need, of course, some random, right? Random generator for points. So let's decide the range. Also we will have a default min and max values for x and y. All right. So this will have to rewrite this, right? Import random, of course. We need random. And we need, of course, so define gen points, right, n, right, and then min, right, something like that, right, random uniform, right, min x, min max y, random uniform for I in range, so let's see, uniform, right, let's see, okay, so random distribution, so uniform distribution, right, for I in range. So this looks okay. This doesn't give you, of course, not generated, this is, you get random a list. So make a list of random list of, right, so this is pretty, good thing to wake up, right? Uniform x, y, x, max y, and I will do probably minus, well, I guess we'll keep them positive for now, right? Let's see how it works. Let's test it, right? Let's test it. Oh yeah, we need to calculate distance. Okay, that's also good, right? And this will be, of course, yeah, mass will be good, right? Define distance between point 1, point 2, square root. Do we need the mass? Of course, we could have used the built-in function, right? Right. So didn't have to import the mass, by the way, right? So okay. So square root, right, of point 1, right, point 2, right. So these points, of course, are tuples, right? They will have two coordinates, right? So we're assuming points have coordinates. Would be better to use name tuples. Would be even better, actually, if you want to make it more clear, actually, right? Maybe we could do that, actually. Maybe let's do that, all right, to make things much more clear. Good morning. Yeah. All right. So yeah. Again, maybe again. So this again dwells into. It's okay. It's morning. So again, to maybe name tuples are sort of like between tuples and sort of like class-based approach. You get the best of the both worlds. So let's actually use that actually, right? So instead of doing that, make a list of endpoints as named tuples, right? So let's first we need to define. So first, right? Now first let's define a named tuple. Yeah. Name tuple point, name tuple point x, y. Right. So example point. Right. Maybe I'll show this separately to show you this. So we'll cover a bunch of topics today at once, right? So let's make one point x1. Now we have dual access. Right? We can use the names or the indexes. So this is really nice. So print, right? One or right. So let's double check, right? So you see this is a little bit nicer, right? Again, so this point we made a new name tuple of point, right? So again, of course, with name fields, right? So it's a little bit nicer. Okay, we'll use that. So we'll use that. Now we can use it here. So instead of using a tuple, we will use here we use point, right? So that's pretty easy to add, right? So point Where is our, yeah, and that's it actually. That's all we have to really do, right? Yeah, easy, right? And so that looks good. And of course here, we don't have to change anything, right? Because we still have this axis. However, this would be point, we could keep it, right? We could rewrite, since these are named tuples, right? These are will be point, right? Point, right? Point. Yeah, and we get float, right? So I'm adding some type hints, so some type hints to help us, right? So instead of this, right? Let's double check first. Let's get some points, right? Pass, we don't need any pass. Let's get 4 points. Gen points, right? On print points, right? And then first 2 points, right? Let's take a look, right? Does it work? Yeah. All right. So we'll have, of course, a lot of floating. Maybe this is a little too much, right? We don't want this is just messing up things. But we could do maybe. So what I'll do is maybe round it up a little bit, right? Let's do that. So I'll do round, and we do like comma 2, right? Comma 2, right? And round, right? Comma 2, right? Something like that. All right, quick and dirty. I hope and of course here I made mistake somewhere. Okay, where did I make mistake? Round, random, uniform. That looks okay. Round. We need one more, I think. Yeah. Yeah. Okay. Now we're good. I think. Let's do it one more time. Yeah, that's better, right? Just looks, cosmetically better. Of course, not as precise, right? And of course, you still get the distance again. Again, we need precision, right? We will do round, precision, right? And our precision is precision. And precision, of course, will be, let's see, square root, not there. Square root also has precision. I wonder, no, it does not have precision. Precision has to go here, right? Not here, sorry. These are, of course, all the setup. All the setup needs to be done first, right? Okay, and we don't have precision, so we have to add here, right? Precision. And again, that's the problem. You start trying to implement some good practices, right? So then, of course, it all ends up, you got to do too much extra work. So let's do now. Yeah. Okay. Now, so we are set. So we have done all the helper functions we need, right? We can make as many points as we want, right? Random uniform distribution, right? As we're assuming these are going to be floats, right? So point will have points, will have floats, but of course, as being Python, we don't really have a hard requirement. These are actually floating point values, right? Remember, these are dynamic, not static typing. It's just pretty much anything goes, right? But at least we have some type hints. Okay, so far so good. So let's do this. Let's implement brute force, right? We have a distance calculator, right? So we have abstracted this distance. We have generated points. So let's do that for. Let's implement our brute force algorithm. We simply check distances between all points and return the minimum, right? That's it. So define brute force points, right? Brute force. So how many points we have? Minimum distance is infinity. Right, floating point in infinity, right? So, assuming we have at least 2 points, assuming we have at least 2 points, we should beat this, right? Beat this positive infinity, right? So for I in range, for j in range, minimum distance is minimum, right, of whatever we have, right, and whatever we are looking at, right? So this is where you can see clearly. You can see clearly here we get n the distances which is of complexity, of course, complexity, time complexity, right? All right. How about space? How much space we need? Well, we don't really need extra space. It's fixed. No matter whether we have a billion points or a trillion points, we only have minimum distance. We still need the points, obviously, but that's given, right? But we don't need any extra data, right? Storage, right? No, we don't, right? So let's check, right? So let's find the solution. Now we can check it. Let's check it. Yeah, brute force on our points, right? Let's see which one it is. So if, let's do that. 3117, right? Of course, maybe better to find which points are those, right? Minimum distance is okay, but maybe we can store the actual point, right? Points, we could store, we have a tuple, points 1, points 2, right? And then the actual distance, right? So, how could we do this, right? So, minimum distance, right? And points we have none, right? And points or corresponding points, or corresponding correspondence is none, right? Those are the points. Those are our points, right? So what we do is, right? But now then, of course, this makes our things, code slightly less. We just can't get by with min, right? We need to have another if here, right? It's basically I do if or self. So instead of this, right? Since we are saving, since we are saving points, we need an if, right? So if, right? If distance less, right? We generate the minimum distance and of course correspondences, right? And of course it'd be nice to actually use them, right? So we return minimum distance and correspondences, right? Right, okay. Now let's do that. So we'll see which ones are the guilty ones. Right. So those are the ones which give us the best results, right? So again, looks okay. X values, Y values, looks about right. Why? Because there's almost no difference between Y values, right, and X is about 30 something, right? So this looks about right. Looks like there's no obvious error, right? Maybe there's some subtle error, right? But do you agree with me that this is not, looks pretty okay? Yeah, so if you were asked to do brute force for this type of problem, right, you could do this, right? Probably, more or less, right? Okay. So how could we improve this? So this brute force. And again, if you only have 1,000 points in real life, don't worry about it, right? We could test it, right? Test on bigger values, right? Let's do some timing, see how long it takes, right? Let's generate 1,000,000 points. Let's generate 1K and see how long it takes, right? So points 1K, right? On points 10K, right? We'll do that. Let's time it, of course, right? I'm gonna do, so we already know this may take a while, so let's time. So time it. Well, first of all, fine. Okay, maybe let's be a little bit careful. Maybe I'm promising too much, right? So points results, right? So print, right? Brute force points 1K. What's going to happen? Okay, 0.3 seconds, right? So looks like we found a real winner, right? Of course, if you think about it, right? Our minimum maximum is 100, right? So you're putting 1,000 points, you're going to be starting getting some really close points by some, basic packing algorithm, right? Because you just, you're running out of space where to put the points, right? So 0.8 is actually a little bit less than I expected, of course. Again, it's just randomness, right? How about 10K? So, first of all, if this took 0.3 seconds, how long should this take, roughly? If you, just roughly thinking, how long it take this 10K?
15?
Yeah, I think, because 0.3, well, 0.3 times 100, right? So times 10 would be 3 seconds, maybe 30 seconds, maybe. Let's live dangerously. right? Let's run this brute force 10K. So I'm thinking half a minute, right? So I'm thinking, yeah, it's working. Again, of course, depends on the machine, right? But yeah, 6, maybe 25 seconds. So first 15 seconds, not yet. Maybe you'll be right. No, 25 seconds. Who has 40 seconds on a? I'm thinking 30. Because of course 0.3, right? But it might be a little bit more, right? Maybe 35. No, I'm okay. Maybe 40. Okay, well, it doesn't look so good. It's going to look worse. 39, come on. Okay, 40 seconds. Yeah, and look at this. What the heck happened here? What happened here is that actually, that doesn't sound right, but maybe it just really, is this really randomness? That seems amazing. What happened here? Let's double check. It says 0, 0. Yeah, but let's see, do we have an error in our code? Doesn't look likely, right? Because we see changes. So let's inspect unique duplicates. Let's check if we have any duplicates in our points 10K. Right? Yeah, counter, right? Items if, right, counter, we count items if value 1. Let's take a look. Yeah, there are actually 3 points which are exactly similar. Oh, wow. So actually let's do this, count it, right? Wow, kind of funny. Right, so again, let's count it. Let's see those duplicates. So counter, points, most common, I don't know, most common, top 10, right? Very interesting. Yeah, so there are 3 duplicates. It kind of seems okay. So well, okay, let's think about this. Is this how likely? This seems kind of to me. We had 10,000 points, right? And how many different values can we have for each point, right? We have a tuple, which could take value from 0 to 99.99, or actually to 100, right? So that's, well, technically for 10,000 values. So that's 1 million. So this looks like a birthday paradox, perhaps a little bit. Again, my statistics are sometimes a little bit rusty. So seems like we might have a little bit of birthday paradox on our hands, right? Seems like, right? The fact seems like we have a bit of birthday paradox here on our hands, right? Wikipedia, birthday paradox, right? Birthday problem. You might have heard of this problem, right? Yeah. It's more likely to have same birthdays than you would think, right, basically. Okay, very good. Okay, right.
There's so many repetitions, like it comes to like...
Yeah, it's like you're almost guaranteed to find, basically, yeah. Again, for those who have seen this, right, at some moment it's just like sharing birthday, like if you have like 50 people, it's like almost like it's like a huge, right, the probability. It seems counterintuitive, but it is, it seems wrong, but actually it's completely true, right? Yeah. Okay, right. So, so this is what we are dealing with here, actually. So kind of cool. But so what can we do? Well, of course, it's not really a big problem. I mean, our algorithm still works, right? We still find the minimum distance. But of course, what I could do is I could generate the points with a larger range, right? So and still I might get there, right? So I'll do n, right? Minimum. Yeah, let's do 1,000. Let's do 1,000 min. Right? So this will hopefully, let's see if we still not, this again might not be enough to avoid the birthday paradox, right? But I'll do 10,000. I'll do 10,000 here also, right? So we have more people joining us, like hopefully. Good morning. Excellent. So now let's do this one more time. So okay, so 0.4 seconds, so 8. So obviously distance, well, kind of expected, right? We still get pretty close, 8, very close. like 9, you know, Euclidean distance. So let's do one more. Let's spend 40 seconds talking about our brute force. So it will take longer. It should not take much longer, roughly the same. I mean, we just, as far as numbers goes, it shouldn't really make much difference. So how close will be? Will we have a double? I wonder. So we have how many possible values? We have, well, technically 100,000 times 100,000. So if you think about it, 100,000, 10,000 times 10,000 is what? 100 million? Yeah, 100 million, right? Yeah. So 100 million different birthdays, right? And we have 10,000 different people, right? Or in this case, it's points, right? So let's see how brute force is finished. Yeah, 0.35 again. Yeah, it's getting close to our points. Okay. All right, so we know how brute force works, but it is certainly for 10,000 points not so good, right? 40 seconds, not so good. So now, of course, our task is to actually to do some divide and conquer, right? So this approach is, again, a typical divide and conquer approach. We split the problem. So you have 2 points. What's the closest distance? It's a trick. It's not a trick question, but it's just an obvious question. You have 2 points. What's the closest distance? Well,
0.
no. I mean, yeah, but it's whatever those 2 points have a distance, right? That's a minimum distance, right?
Ah.
Yeah. You have 2 points, right? You have 1 point. You can't really give an answer, right? But you need at least 2 points. But then you just take the answer. So that would be our base case, right? If you could somehow divide down to 2 points, right? We have our winner, right? It's 2 points. Actually, in practice, you usually start with 3 points. We can use our brute force for a very small amount of points, actually, right? Sort of like how team sort uses very inefficient sort, insertion sort for smaller amount of points, only moving to merge sort later. Here also, we can use maybe brute force for 3 points, maybe 4 points, I don't know. Let's see, right? So, but also the approach will be tricky a little bit. Oh, sorry. Oh, great. I don't see anything. Do you see anything there?
No.
Oh, great. Where's our, which screen do I don't see anything either. No, the question is, where is the monitor? Great, yeah, it just yeah, that's great. No, I need to find the, where is the, there it is. Yeah, that's great. Okay. Do you see anything?
Yes.
Okay. Do I see anything? I see something else. All right, that's good. No. So division, so that we have solved this, right? But here already my notebook already says a little bit, ahead of time. But the question is, what do we do? How are we going to do? What are we going to do with when you have more than 2 points, right? So, okay, 3 points we could use the brute force. But if you have 2 subsets, right? We are going to assume we know the solution for each subset, right? We know for one set we have the minimum or the other. So we have what? We have 3 choices. Which one is going to be winner? The easy one we have, okay, we compare minimums from both sets, right? And take whichever is minimum, right? Okay, maybe I'll do paint. I'll do again my friend paint, right? With the color points, right? 1, 2, I don't know, 3, right? Amazing, right? Maybe so, and I'll do some sort of like line, right? So we assume, of course, this is a minimum, right? Right, this is min, right? Min 1. All right, 1. Okay, and let's do some other points. Some are here, right? We have point here. I need a better brush. Oh, maybe a bigger brush. Okay. Oh yeah, that's better, right? And I have another point here, right? Okay. So again, we have our distance, which is, this will do here, right size. That's our minimum, that's our min 2, right? All right? Okay, so these are 2 subsets, right? Now, So we have two choices. So min 1, okay, so it looks like min 1 wins here, right? So we take the min 1, right? We have these two subsets, right? Again, take this, right? So this is our subset 1 and subset 2, right? All right. But is that all, or is there another case? What's another possibility? Where else could we get the winner? If you think about it, like we compare, because these are all points of. Originally, we had all the points are all from the same set, right? We just start dividing, right? So divide and conquer. Now we're trying to merge them together, basically, right? So what's the third possibility? Well, let me help you a little bit. Let's see if I can do this here. Let me do this, right? Control X, Control Y, right? And I'm going to do this. Well, not so good, but I can start doing it, right? Still probably not going to do it, but maybe I can. No, I can't, I guess. But yeah. But the thing is, of course, if I start moving together, right? Right. Control X, right? Control Y, and now, do you see the issue, right? Right now, we have these two sets of points, 3 points here, 3 points here, right? We have min 1, min 2, we have found it already, but what's the third possibility?
The other points.
So basically, these 2 points will make a new minimum, right? So, and this is what makes this algorithm harder, I think, to solve, right? Okay, come on, where's my line? Where are my lines? My drawing skills, I love paint, so pencil. Okay, there you go. So this is our new min 3. Min 3, right? So we need some way of checking how to find this, right? And then of course it thinks, okay, but then then aren't we at square one? That's the thing, right? We have to check all the points, right? Maybe, from both sides, right? Are we actually gaining anything? Yeah, and if you're doing brute force approach, then we don't really win anything, right? But it turns out, of course, we do have some extra information about this stage, right? We only have this minimum information, right? We don't have to check all the points, right? So if we could keep these subsets in some sort of order, right? What's the obvious one, of course, would be the use x-axis, right? Of course, also we have y-axis, right? Right, x-axis, we could sort them, keep them in sorted order. Well, then we wouldn't have to, if you have to start looking too far, right? If you see, our candidates only will be potentially in this area, right? So if you check this area, right? Then we will know whether we have a potential winner from this merging. Otherwise, if there's no candidates, no suitable candidates, we would go take the minimum, existing minimum, one of those, which is really easy. So yeah, so in this case it is a little bit tricky, and of course again, checking, right, again, how many to check actually, right, I think you need to check 8, I believe, or 5, I remember, no, I can't remember exactly, but let's double see how the solution works, right, we will get to that, right, so, preprocess, so we'll need some preprocessing, right, x, right, on split, right, and again conquer, right, recursively find and merge, right. So and then of course we need to strip, right. So it is n log n. So the question is, what is n log n? Well, we take n time to split the points, right. So the problem is we also need to sort. So already our bottom, we already know our general sorting algorithms, good sorting algorithms, n log n, right, general, right? So that's only our bottom approach. But let's see it here, let's see, this is like a high level overview, let's see if we actually can do it, right? So, alright, so this is summary, but let's see if this works. Let's see if plotly is included, I hope it is. Let's see if we can show it. Let's see, this is actually a solution where I'm not sure if plotly is included in this code space. Let's take a look. Let's do random C24, right, it's new year. Oh yeah, I don't have plotly here, but we can install it, right? No problem. Pip install Plotly. Yeah, right. Yeah, virtual environment. Let's see. Main. I think so, right? Scripts virtual environment. Pip list. Let's see what we have. Yeah. All right. Pip install Plotly. Let's see if this works. Oh, I have Plotly. So why doesn't it not here? Virtual bin. Maybe deactivate. Let's see. Oh, right. So why isn't Plotly working? I wonder. No module made Plotly. Requirement is because this is cond. I believe this is cond and this is virtual environment. Okay, we can do something silly. No, we don't want to do this silly. Maybe we can use. Okay, let me change the kernel. Okay, put another kernel. Existing Jupyter server. Yeah. Can we do that? Hello. Yeah, I can do that. No, not that. This is what we have, right? This should be enough, hopefully. Unable to connect to remote server. Maybe not what we want. All right, let's do it one more time. All right, so let's do pip install Plotly. I'll just do lazy because the probable issue is that of course the terminal is on, looks like it's conda, and this is actually using the virtual environment. So I will install this pip install Plotly. All right. Let's see if this works. Yeah. Okay, that will work. All right. Again, if you're on Colab, you won't have this issue. Plotly is a great library for visualization. I don't know if any of you have used this. It's a good library. So it's 9:45. So let's take a break while I install this. So we'll continue at 10.